I will be starting with the problems now. I will first be discussing the problem cow and fields. So in this problem, basically we are given a graph. Hello, am I audible? Okay. So in this problem, we are given a graph with n fields and m edges. So we have to find the shortest path from node 1 to node n. And there's an extra condition that we can add exactly one edge or maybe zero as well between any of the two special fields. They are case special fields, they are given over here. So basically, I will give an example first. Suppose this is a graph. This is vertex 1 and vertex n. We have to maximize the shortest path between vertex 1 and vertex n by adding exactly one edge between any two special fields. We want to maximize the shortest path as the farmer wants the longest distance. So basically, we can color special nodes with red color. So let this and this be a special node. And now we have to choose any two and add an edge between them. So basically, we will first find the shortest distance from node 1 to all the other nodes, and also the shortest distance from node n to all the other nodes. Let ai be the shortest distance from node 1 to the ith node in the original graph, and bi be the distance from node n to node I in the original graph. So if we add an edge between uh, two special vertices j and k, then the distance between them using that edge will be minimum of aj plus bk plus 1. Go to the jth vertex first, and then we use that edge to go to the kth vertex, and then to back to vertex n. And the other possibility is we go to vertex k first, and in this case it will be ak plus bj plus 1. Now we have to choose j and k belonging to the special vertex set such that this value, this minimum of two terms is maximized. And of course, we have to minimize the answer by the original shortest distance between 1 and n, which is an. So, did you all understand the problem statement and this shortest path formulation? Okay, so now we can look at two cases. First, in which the left term is equal to or lesser than the right term, we can write aj plus bk is less than equal to ak plus bj. And now the trick is to manipulate the terms such that the values of node j are on one side and values of node k are on the other side. So we can write aj minus bj is less than ak minus bk. So if this value is smaller, aj minus bj is smaller, then this node will this value will be used, and if the signs are reversed, then this value will be used. So basically we can sort all vertices, all special vertices by AI minus BI. And now, suppose this is the sorted order of the vertices. Now, for the left one, since this one is smaller, we will go to that vertex first. So suppose I occurs before j in the order, sorted order. Then we will go from 1 to node I using AI steps, then to node j using new h, and then we will go to node n using bj steps. And we get AI plus bj plus 1 steps. And now, if you notice these terms, the two terms are independent. So we can go from left to right and maintain the maximum value of AI till now. We can find the maximum value of AI till now. And then suppose we are at this vertex. We will max the answer by, let this be k. We will max the answer by bk plus maximum till now, maximum value of AI for all the vertices before k plus 1. And we can maximize the answer by this value. And of course, in the end, we will minimize the answer by the shortest path from 1 to n in the original graph. So I will show you the code. So basically in this, we are finding the shortest path from node 0 and node n. And now we have sorted the vertices by this I minus this 2i, which is AI minus bi. And now, as I told, we will maintain the maximum prefix over here, and we will maximize the answer by this value. So did everyone understand the problem solution? If you have any doubts, you can ask. So this is basically an exchange argument trick where we can sort by a value, and it's optimal to take in sorted order. So if nobody has any doubts, I can go to the next problem, which is yesterday's contest div 1c and div 2e. So basically, here there are given n albums, and each album has some tracks. So there are n albums. Let this be the album. So an album is a sequence of track. So let this be album of 5 tracks, and each track has a value associated with it, which is the coolness of the track. And now the problem asks you to order the n albums in a order, and in each and for each album the tracks are played in the order of specified. You can't change order within the album, but you can order the albums. You can't change the order of the tracks. And now in the final sequence, suppose the coolness order of all the tracks is like this. Then we need to count the number of values which are greater than all the values which have occurred before them. So basically we have to count the number of prefix maximums. So obviously 1 is a prefix maximum, then 5 is greater than 1, but 4 is smaller than 5. 3 and 2 are also smaller. 6 is greater than 5, and 7 is greater than 6. So the value here is 4. We need to maximize this value by ordering the albums, and the constraints are n is 2e5 and the sum of all the number of tracks is also 2e5. So we have to think of a linear time or n log n solution. So did everyone understand the problem? Okay, so I will now explain the solution. So I will first give a hint. Now suppose we have a track. Instead of writing the values, I will plot it in such a way that I will go up if the value is greater and down if the value is smaller. So suppose the values are associated like this, where higher denotes higher value. And now if you notice, if inside a album, a track has lesser value than something which occurred before that. So for example, this is redundant since the value of a left one is greater than it, and it can never be a prefix maximum since the order of a tracks in a particular album is always the same. So we can remove these and we can get an increasing sequence in each album. So we can get a increasing subsequence of a album. Does everyone see why this happens and why we can just take the increasing sequence by going from left to right and adding an element if it's greater than the rest? So did everyone understand the increasing sequence part? Okay, now we have n sequences of this sort. We have n sequences, n increasing sequences, and we need to order them in such a way that the number of prefix maximum is the largest possible. Now, one more observation, if you have noticed, suppose there are two tracks I and J. Let the last value of the track be largest value be Ci and Cj. If Ci is greater than Cj and ith album is played before the jth album, then there would be no prefix maximum due to the jth album. So, for example, this is 9 and this sequence is 238. If we play 238 after 9, there will be no new prefix maximums, and so it's always optimal to visit a subsequence of the albums in order of the increasing order of CI. So, for example, we will now look at the albums which contribute to a prefix maximums and we will view them in increasing order. If an album does not contribute any prefix maximum, it's useless, so we can ignore that. Now, suppose that these are some albums which contribute. We will actually sort the albums by CI. So let's, without loss of generality, CI less than CN. So basically, we have sorted them, and now a subset of them will contribute some value, and we have to look at the subset which maximizes this value. So, did everyone understand why we take in sorted order? You can ask any doubts if you have, unmute and ask. So, did everyone understand this? Hello? Okay, so now we will look at a subset of them and take them in order. Let the ones contributing, I will underline them. Now suppose these are contributing, then I will explain again. If it's contributing, then the CI value must be lesser for all the previous tracks, and hence only a subset of them contributes a value, and we take a subsequence. Basically, we can't obviously do CI as C2 after C1 and like in order. Then many tracks would not contribute the optimal value. So now suppose that we will do a dynamic programming. Let DPI be the maximum value, maximum number of prefix maximum possible, such that the last track, last album played is the ith album. So basically, if we are currently at the jth album, and we can iterate over all the previous albums, DPI I is less than j, and we will add the number of values in the jth album which are greater than CI. Now, since it's an increasing sequence, all the elements greater than Ci will contribute a value. So we will count these value and add it. Now, if you see, this will be quadratic n square, and we cannot do this. This will be greater than n square, and we cannot do this since the constraints are n is 2e5. Now, what if we could fix the value, the smallest value of in the jth album, which appears, which contributes the prefix maximum. So suppose in the jth sequence, we have elements a is less than b is less than c is less than d. Now suppose that the all the elements greater than or equal to c contribute to the prefix maximum. Basically, we need to now find all this. We will iterate only over all ci with less than value less than c, and we can maximize dpj by dpi plus 2, and so on. We can fix the element and then add the number of elements greater than or equal to it, and iterate only over dpi which have last value less than that element. Now suppose that the ith track has, ith album has si elements. We can fix one, and since the, if you notice, we have sorted the array, so we can binary search for the last value which have values less than our current element. We can binary search and take the maximum of dp between them. We can maintain prefix maximum of the dynamic programming and maximize our answers. Now the complexity for the while processing the ith album will be si log n, and if we sum this, it will be 2e5 log n. Since it's mentioned obviously that the total number of tracks is less than 2e5. I can go through the code. I will go through the code as well. So, does anyone have any doubts in this? Okay, I will explain it again. Now, in this, we are counting the number of values which are greater than Ci. Now, what if we could fix the number of values which will contribute to the prefix maximums? So, suppose a suffix of size, let let it be a increasing. I will make a bigger increasing sequence. Now suppose that from the ith elements all are contributing to the prefix maximums. Now we need Ci to be less than Aj over here. So instead we can fix this value and find the maximum of all dp's with Ci less than the fixed value. We will fix this and find the maximum of all dp with value Ci is less than I. Maximum dp. with Ci is less than the current value. Now we can find the maximum value by looking at the first element with value Ci is less than this. Since the array Ci is sorted, we can find the first value. Suppose it is this. We have to find the maximum DP of all the first three elements. And then we can maximize the answer by m minus j plus 1 plus maximum dp. We will add this to the answer and we can maximize dpi by this. So did you understand now? Yes, since that number is lesser. So if we go over previous one, these are order n, but here it is order of number of elements in the ith track. So which was si, and so it will be si log n. And now summation of si is less than 2e5 as per the problem statement. So this will be around n log n and it will easily pass. I will now go over the code. Okay, so in this part, we are basically taking an increasing sequence of all the albums. As I first told earlier, we will take only increasing sequence. We will sort the all the albums by the last value, maximum value. And now we do a DP, where DPI denotes the maximum number of prefix maximum such that the last album played is the ith album. So here we initialize the condition dpi is the number of elements in the increasing sequence, and now we iterate over the elements in the ith album and binary search, then binary search for the first for the highest index which has last value less than this, and so on. We can maximize the dp and then we just maximize the answer again and again by dpi and just print the maximum one. So did you all understand? So did you all understand the solution? I can give you a walkthrough through an example if you want. Okay. We'll move on to the next problem now, which is Orac and Medians. This was used in a mashup contest. One second. So in this problem, we are given an array of size n. We are given an array of size n, and we can do an operations on the array. In one operation, we can select a range. We can select a subsegment and change all the elements in the subsegment to the median of the subsegment. And if there are an even number of elements in the subsegment, say the elements are 3, 4, 6, 5, we will take the second one if the size is 4. So basically, if there are n elements, we take the n plus 1 by 2 floorth element in sorted order. So basically, we need to change all the numbers to a certain k which is given in the problem statement, and we have to tell if it's possible or not. We don't need to construct the solution or anything. So did everyone understand the problem statement? Okay. So now in this one observation is that if you have an element A and then there is an element B, if you apply the operation on two consecutive ones, the numbers get changed to min A comma B, min A comma B. One important thing is we have to change all the numbers to K. So there must exist some element in the array which is equal to K. So if no element is equal to K, the answer is no, obviously. Now we will look if there are elements equal to K. Okay, it seems like I was in mute. So I will repeat. So suppose there are two consecutive elements A comma B. We can apply the operation on them and change them to both to min A comma B and min A comma B. Since 2 plus 1 by 2 floor is 1. So we take the smallest one. We can apply the operation and on two consecutive one and get this. Now obviously there must be some element in the array which is equal to K. Since we want all the numbers to be equal to K at the last and no new elements come after applying the operations. Did you all understand this observation? Okay, so now I will show how we can get the all the elements equal to K and in which case we cannot. So suppose there are two consecutive elements equal greater than or equal to K. So we will first try to get all the elements greater than or equal to K. So why I will show, suppose this element is K and all these are greater. We can do the operation on two consecutive ones and get all equal to K. So it's almost same only. So suppose there are two elements greater than or equal to K and an element less than K. If we apply the operation on these three, all the elements will get changed to a number which is greater than or equal to K. And so on. Suppose these two are greater than or equal to K, we can increase this sequence one by one to the right if the elements are less than K. If they are equal to K, we just change them to all to K using the operation of 2. And so on. We can extend the segment till the end and we will get all elements equal to K. Now the second case is when there are no two consecutive elements which are greater than or equal to K. So suppose these are the elements greater than or equal to K. Now suppose there are at least two elements smaller than them between any two consecutive ones. So suppose these are two. Now if we take an operation selecting all the elements, you will notice that the median will be the smaller element which is less than K. So suppose we take this, you will notice that the number of elements smaller is always greater than the number of elements greater, and all the numbers will get soon changed to less than K and we cannot get new numbers equal to K in the process. So in this case the answer is no. And now the last case is, now there are no two consecutive ones and the distance between at least one of them is less than 2. So suppose then it must be exactly 1. We have two numbers greater than or equal to K and one less than K. We can apply the operation on them and all the numbers get changed to L with L is greater than or equal to K, since the second smallest element in the array is greater than or equal to K. And now the case is similar to the previous one, since now there are two elements which are greater than or equal to k, and we can extend the segment to the left and right. So did you all understand the three cases over here? If you have any doubts, you can ask. Yes, can you repeat? Which one? Okay, the one in which there is exactly one in between. Okay, so now if there's exactly one less than k in between, we can apply the operation on the subarray of size 3. The median is the second smallest element. The second smallest element is greater than equal to k, since there's exactly one less than that. So we can apply the operation and change all the numbers to greater than or equal to k with L greater than or equal to k. Now if you notice that there are two consecutive ones which are greater than equal to k, and we can now get to the previous case. The case one which we took, in which we are greater than or equal to k. In this we were able to convert the entire array into an array or equal to k for all elements. So now did you understand the third case? Okay, so someone is asking, and I will give some more examples to make you understand. So suppose case 3, and we have this array. Now we will take these are two consecutive elements which are greater than or equal to 3. We can take the segment of size 3. So suppose we take 452, all gets changed to 4. Now we can take 441 and all will get changed to 4. So this will also become 4, and so on we can get all 4. Now this one is exactly 3, and since we want all elements equal to 3, we can apply the operation on two elements to get the minimum of them. So we can apply here and get 3 comma 3, then again on 3 comma 4 and get 3 comma 3 comma 3. And now we can extend to the left as well. We will take a subarray of size 3, 2 comma 3 comma 3, and the median is 3, so this will become 3, and so on. This will also become 3, and now since k equal to 3, ai equal to 3 for all I. So did you all understand this case, the example? Okay, now I will take the example of the second case. Let case be 3 only. Let this be the array. In this, if you notice, if we take there are greater than two numbers between any two numbers which are greater than k, there are at least two numbers. Now if you notice, if we take any subarray in this, so suppose we fix it at this ith 3 and we take till the jth 3, then there are j minus I into 2 numbers lesser than that, and j minus I plus 1 numbers greater than k. So now if you notice that this number j minus I into 2 is greater than j minus I plus 1, since j minus I is greater than 1, this number is greater than or equal to this, and the median will be from the this one. So the median will always be the smaller element, and any operation will result in median less than k. and we cannot get any number equal to k. So did you all understand? Okay. So the third case is quite similar. Suppose we have three numbers, two are greater than or equal to k and one is less than that. So now if we apply an operation on this, we can get 3 comma 3 comma 3. And now we come back to the first case where there are two elements consecutive greater than or equal to 3. So did you all understand now the complete solution with example? Okay. Now I will show you the code. The code is actually very simple. Now we first check if there's an element equal to k. If that there's no element equal to k, we just print no. We handle n equal to 1 separately to avoid any bugs. Now we check if there are two elements such that both are greater than or equal to k. If that happens, we can set the answer to 1. Now we will check if there's exactly 1 in between two consecutive ones. So in this print, we can print yes or no. I will send you all the submission links also later. So did everyone understand the three problems discussed till now? So did everyone understand all the three problems? Okay, so should I move on to the fourth problem? Okay, now I'm moving to the last problem, which is bridges. This is a problem from Adcoder which I sent in the problem set before. So now in this problem we are given a graph. Basically we are given m edges between ai and bi, and now we have to construct a graph with two n vertices in, and now there are vertices of different color. So now if there is an edge between ai and bi, we have two choices here to connect ai with bi plus n. Basically plus n denotes that we are going to the other n vertices. We add n over all these vertices towards the right. There are two sets, or bi with ai plus n. So these are two options, and we have to connect in either one. We are also given n additional edges which are mentioned over here, where we connect I with I plus n. All edges are bidirectional since it's an undirected graph. And now we have to choose the out of these two in such a way that the resulting graph with two n vertices has minimum number of bridges. So bridges are an edges which, when removed, disconnect the graph. So if you remove that particular edge, the graph gets disconnected. So did you all understand the problem statement? Yes, this problem is harder than the previous ones. So did everyone understand the problem statement? Many of you would have read the problem before as I had sent earlier. If you don't understand the problem statement or the definition of bridges, you can ask. Okay, so I will give some ideas. So suppose an edge, let this be a original graph. Suppose an edge is in bridge in the original graph as well. Like this edge is an bridge in the original graph. If you notice that in this graph also there is nothing which can prevent that edge from being a bridge. Since if you remove that edge, so let this be a edge connecting the first half to the second half. This is I and this is J. I and J are bridges. So if you notice that if you can't have them in a cycle, since where they were a bridge in the original graph as well, so you can't really have a cycle even with the n added edges. So did everyone get why a bridge will remain a bridge? Okay, so you don't need to know how to calculate bridges in this problem. You only need to know how to, like, what is a bridge. Basically, the definition works. Okay, so I can show you how to calculate the bridges and how to find the bridges and what is a bridge. So, did you all get the definition of a bridge? A edge which, when removed, will disconnect the graph into connect different components. So, did you get the definition? Okay, no. So now I will teach you about the DFS tree. It will be used in solving the problem, and it's also used to find bridges, which is unrelated to this problem. So suppose you do DFS on a graph. You take a vertex, you go over all its neighbors, and see which ones are visited before. Which are not visited before, you run DFS on those, right? So suppose this is a graph. Now suppose this is vertex 1, you are 2 is adjacent to 1, you go over 2 and run DFS on that. Now you go to 3 from 2, come back. Now suppose 4 is adjacent to 2, both 2 and 1. So you go from 2 to 4. Now if you notice, when you are at vertex 4, 1 is a neighbor of that, but you have visited it before, so you don't run DFS on that. So this is a case of a back edge. The n minus in a graph in a connected graph of n vertices, n minus 1 edges will be visited, right? So in DFS I, so suppose this is a function, and now suppose you recurse over DFS j node to node j from over here. Now the edge from node, the connecting node and j is a forward edge, and this is a back edge. So these are forward edges. So suppose there's an edge from there are two edges between node 1 and 10. Now the one will be a forward edge and one will be a back edge. So did you all get what are forward edges and backward edges? Okay, and one interesting thing is a back edge can never be a bridge. This is because if you remove all the back edges also, the graph is connected since you visited all the vertices. Only a forward edge can be a bridge. Now suppose this is a forward edge. And now in the DFS subtree, you form a tree. There's a back edge going from its subtree to its ancestor or itself. So suppose to one of its ancestors, uh, this is a subtree, and there's an edge from a back edge from one of its descendants to one of the ancestors of the node visited first of the edge. Now in this case, this vertex is not a bridge. This is because see, let this be an edge. If you remove this also, the graph is connected. Since this is in a cycle, a bridge can never be in a cycle, right? So did you all understand this part? Why a bridge can never be in a cycle? And so we need, if there's an edge, bridge edge, with no back edge, so there's no connection between its subtree and the rest of the tree. There's absolutely no way to go from the subtree back without this edge. This edge is a must, so it's a bridge. So did you all get this part? Okay, so now calculating the back edge and forward edges is not a big deal since it's just DFS. You mark, if you visit node J from a node, then you mark that edge as a forward edge and all rest are back edges only. It's an undirected graph, so there's no possibility of an edge from a node which goes to another node. You can't have a triangle like this. You can't visit the same node twice, right? So we can only visit it once as a forward edge. Back edge you can do infinite times, obviously. Yes, back edge can never form bridge. All back edges are in a cycle. Since it's a tree, the forward edges form a tree, and the back edges are extra edges. Basically, it's a spanning tree. But you don't take an arbitrary spanning tree to prevent cross edges going in a horizontal direction. You want them to go to an ancestor only in the tree. So you do a DFS. So these are the forward edges, and suppose this is a back edge. We can add an edge. This is a back edge. Now going back to the original problem, we connect AI with BI plus N or BI with AI plus N. Now, sir, we showed that if a edge is a bridge, it will remain a bridge in the final graph as well, in the constructed graph. So now suppose an edge is in a cycle. So we are talking about this particular edge. These are forward edges and this is a back edge. It's in a cycle in the original graph. So now if you take, let this be A, B, C, D. So if you add an edge from A to B plus N, P to C plus N, C to D plus N, these are unidirectional edges, by the way, so don't get confused. Now, if you notice that, or if you orient all the forward edges in the first type only, if A is an ancestor of B, then you add an edge from A to B plus N. And now notice that I and I plus N are also connected. By the graph, we are given n additional edges in the problem only. The vertex J is connected to vertex J plus N. So now if you notice, there is an edge between these. Now, since we want, there's an edge between D and D plus N also. Now, since we want all these edges to be in a cycle, if they are in a cycle, they cannot be bridges. We need to minimize the number of bridges. So now, if we consider the D to A edge, we have two choices. Either we add D to A plus N or A to D plus N. Now, if you notice that if we add D to A plus N, then A plus N is also connected to A and this will form a resulting cycle. So did you all get why these edges which are not bridges in the original graph cannot contribute to getting bridges in the final graph? So did you all understand the cycle formation? We always take the first option. We orient the edges in this way: A to B, B to C, C to D, and we orient all back edges backward. So we take the presentation, the choice of the edge using the direction over here. From the first one, we take the from the first n vertices and we connect to the second one to the second n vertices. So did you all understand this part? Yes. So we have formed a cycle from A to B plus n, then B, back to C plus n, C, B plus n, D, A plus n, and back to A. This is a cycle. So none of these edges are bridges. Now we are left to consider for a fact. We also need to check there are additional n edges I to I plus n. We need to it's always better if we can make these edges also not bridges. Now notice that in the graph, if an edge is connected to at least one non-bridge edge, then A will be connected to A plus n in a cycle, B to B plus n, C to C plus n, and D to D plus 1. So all these are in a cycle and these also don't contribute except for the case when it's a bridge. So for example, let J to K be a bridge. This will contribute to a bridge. And now suppose it's not adjacent to any other edges which are not bridges, then it will also might contribute to another bridge. But we proved earlier that a bridge will always remain a bridge. So did you all understand this part? So did you all understand the part where we connect the edges in a cycle? We are able to construct a cycle since there are an even number of edges, so we come back to A. It's a bipartite graph. Yeah, so now we just need to find the forward edges and backward edges and orient the cycle in this way. Basically, in the original problem, we need to construct a string of 0 and 1. 0 if we take the first option and 1 if we take the second option. Since now we only need to minimize the number of bridges, we can easily do it. Now I will show you an example. I will show on this. In this, there's an edge from 1 to 2, 1 to 3, 1 to 3, 2 to 3, 3 and 4, 4 and 5, 4 and 6. I've duplicated it. It's connected here. Now suppose we do DFS over here. Suppose we go from 1 to 2 first, then 2 to 3. Now at 3, there's an edge back to 1, so it's a back edge. Now we go from 3 to 4, 4 to 5, 5 to 6. This is an again an back edge. So now we add an edge from 1 to 2 plus n, 2 to 3 plus n, 3 to 4 plus n. And suppose this basically we generalize this. If there's an edge from A to B, we orient the edges in such a way: forward edges forward, backward edges backward. Then add an edge from A to B plus n. So if the original order in the input is a comma b, we choose 0. If it's b comma a, we have to choose 1 to add an edge from a to b plus n. So did you all understand the example? Okay, thank you for listening. I have discussed all the problems I plan to discuss today. Thank you.